All right, hey, how's it going? um, so I'm sorry I had to be out again. This should be the last time in quite a while. I have my second root canal. That's what it's called. Anyway, wish me luck with that, and hopefully this video is not too boring to watch. Hopefully you guys find it interesting. But here we go. Um, you can see here that we're starting chapter 6. It's on sampling distributions. It's a topic that I guess at points can become pretty confusing, but it's really important. It's kind of the whole point of statistics, honestly, is you want to figure something out about an entire population. So what you do is you draw samples from the population, a reasonable number of sort of observations, and from that reasonable number of observations or your sample, you're trying to make inferences about the larger population. And we do that by taking not just one sample, but many samples, and seeing how those samples behave so that we can make good guesses based on what we're seeing in those samples about the population. So anyway, we'll go through that. We'll see how it goes. Um, Maybe the most important thing is seeing this second check mark here. It says bring your Chromebooks because tomorrow we're doing an activity. Now, I don't know if that activity will have to be cut due to the snow day, due to, we think tomorrow's going to be a 2 hour delay. But suddenly, if we're losing time all over the place, maybe we won't do this activity. But please bring your Chromebooks anyway, because it should be good. Um, Everything else is probably out the window a bit. It says our quiz is Friday. That probably is no longer true due to the snow day. But we also have the progress check coming up as well. We'll need to talk about that. I won't talk about it here. We'll talk about it in person when I see you guys. But that's coming too. But without further ado, let me just get into lesson 6.1 on sampling distributions. Off we go. So again, by the end of this lesson, you'll need to understand a couple of vocabulary words, a parameter versus a statistic. We're going to need to create a sampling distribution using all the possible samples drawn from a small population. And then we'll be able to use the sampling distribution of a statistic to evaluate a claim about a parameter. Okay, and some of this will feel like it's stuff we've done before, because honestly, we have. But again, we'll revisit some of these ideas. We'll go after them with a little bit more depth than we have before. All right, so real quick, bit of vocabulary. So what is a statistic? What's a parameter? A statistic is a number that describes some characteristic of a sample, whereas a parameter is a number that describes some characteristic of the population. Pretty easy to remember, honestly, because you can remember the S&P rule. A statistic is for a sample, and a parameter is for a population. See how the S goes with the S and the P with the P. Now, what do these things actually measure? Well, they could be anything. You could take the mean of a sample, and that would be a sample statistic. You could take the proportion, which is like a percent. That if it's drawn from a sample, then it's a statistic. Standard deviation could be a statistic. Basically, any measurement that's drawn from a sample is called a statistic, and any measurement that's drawn from a whole population is a parameter. So again, you see the examples of mean, proportion, standard deviation, but range, interquartile range, whatever. They all could work. Right, on the next page here you see your first sort of just example with those pieces of vocabulary. It says to estimate the mean income of U.S. residents with a college degree, the current population survey selected a random sample of more than 60,000 people with at least a bachelor's degree. The mean income in the sample was $69,609. How close is this estimate to the mean income for all members of the population? So now they don't actually go on to answer that question, but the question that they are asking is describe the population, and then describe the population parameter, then describe the sample, and then describe the sample statistic. So here in pink it says for the sample of college graduates contacted by CPS, the mean income was $69,609. So that mean income, that's a sample statistic. it says the number 69,609 is a statistic because it describes this one sample. It says the population that the researchers want to draw conclusions about is all U.S. college graduates. So this one here in green, that's describing who the sample is at all. And in blue it says, in this case, the parameter of interest is the mean income mu of the population of all college graduates. So again, the parameter is a measurement taken from the whole population. And who again was the whole population? The whole population that we wanted to find information about was U.S. residents with a college degree. And again, when you're describing the sample or describing the population, you basically want to be as accurate as the question allows. So you can't just say residents with a college degree. If it specifies that they're U.S. residents, you must include that too. As much information as they include, you should include. Maybe even right down to the fact that when they say college degree, they mean at least a bachelor's degree. All right. So here's another problem you can try yourself. So for number one, it says, well, first of all, what do you have to do? You have to do the same four things we did in the last problem, which is just identify the population in words, then identify the population parameter, then identify the sample, describing it in words, and then the sample statistic. So number one says, a Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. So again, I don't know how much time you want to spend here, but you probably want to pause the video and try to respond to those four things real quick. Those four things being describe the population, describe the parameter, describe the sample, and describe the statistic. So pause the video and then we'll go over it. Take a minute. Okay, hopefully you took a second to think on this yourself. But as far as who's the population, we'll just read through. It has nothing to do with the Pew Research Center. They're the group who's doing the study. Remember, the population would be the people that they're actually interested in learning about. So who would the population be? The population would be, well, not the 1,102 12 to 17-year-olds. They're going to be the sample drawn. The population is going to be all of the 12 to 17-year-olds in the United States. That should be what it says down here. So all 12 to 17-year-olds in the United States. Now, to find the sample, the parameter. So the parameter is the thing that they're trying to actually measure. And what they're trying to measure is the percentage of the what are they called? Just the people. So the percentage of people that have cell phones. So that's a population proportion is what you'd want to say. So the parameter is the proportion of all of the 12 to 17-year-olds that have cell phones. So again, we want that word all because the parameter has to refer back to the population. Okay, so now describing the sample in words. It's going to be language virtually the exact same as the population, but this time you're going to actually say how many were chosen at a time. Other than that, it should feel very similar. So the sample is going to become the 1,102 12 to 17-year-olds contacted. Contacted by who? The Pew Research Center. You don't need to include that, I guess. But who contacted them? The Pew Research Center. All right, and what's the sample statistic? Well, again, it should very closely match the language that you used for the population parameter. Since the population parameter was the proportion of all that had cell phones, this time we'll say the proportion of the 1,102 12 to 17-year-olds contacted who have cell phones. Yep, the sample proportion. Yeah, sounds good. Okay, so the next one should feel very similar. It says Tom is roasting a large turkey breast for a holiday meal. He wants to be sure that the turkey is safe to eat, which requires a minimum internal temperature of 165 degrees Fahrenheit. Tom uses a thermometer to measure the temperature of the turkey breast at 4 randomly chosen points. The minimum reading he gets is 170 degrees Fahrenheit. So what's the population? Well, what's Tom interested in learning about? He wants to learn about the internal temperatures of his turkey, right? So the population should be the internal temperature of Tom's turkey at every possible location. That's the population, would be every possible spot on the turkey, you find the internal temperature. Let's see how they worded that. All possible locations in the turkey breast. Yes. Sounds good. Okay. Then what's the parameter that we're looking for? So again, the parameter is what we're actually measuring, which is the internal temperature at every possible location. So yeah, okay, that sounds fine. All right, and then what's the sample? Well, the sample would be the few places that Tom actually measured. So again, if we read back through this, it says that Tom uses a thermometer to measure the temperature of the turkey breast at 4 randomly chosen points. So that's the sample, is just those 4 randomly chosen points where Tom chose to measure the temperature. And so finally the statistic would be the sample minimum of 170 degrees Fahrenheit. Okay, so hopefully that makes sense, how to distinguish the population and the sample, which we did that all the way back in chapter 1, and then how to describe the parameter and the statistic. So hopefully that feels good. All right, so next, it says the process of statistical inference involves using information from a sample to draw conclusions about a wider population. Again, that's probably one of the biggest ideas in statistics for sure. It says different random samples yield different statistics, and we need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. We can think of statistics as a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. So what does that process look like, by the way? Well, you have a population, and to try to actually talk to every single person in that population to get to a true population parameter is pretty impossible often. So instead what you do is you draw a sample, and then from that sample you can pull out some representative piece of data, whatever it is you're trying to measure. You can measure it for that one sample. Then with that you can make an inference about the population, which brings us back. So it's this almost this circular thing. You already knew what your population was, but they were too big to really fully understand. So you draw a smaller sample where you can more reasonably measure some kind of sample statistic. And then if you've drawn a good representative sample, and if you've gotten a little bit lucky, then that sample gives you information that goes back to the population. And that's a good thing. Let me just keep moving on. All right. So the sampling distribution now is what I was stuttering over just a second ago, but I was kind of about to get ahead of myself when I realized we'll do it right now. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So that idea, if I go back here now, what I was about to say was just taking one sample wouldn't be a very good idea because we know that samples can have a natural variability. So if I get very unlucky, if I was trying to measure heights, I may end up with an estimate that's very, very low if my sample was sort of skewed to the left. I may get an estimate that's too high, and I might suddenly think that a certain group of people is taller than they are just because the sample that I chose was kind of skewed to the right. So a way to mitigate that is you don't just draw one sample, you draw many, many, many samples, okay? And that is what becomes a sampling distribution, all right? So it says here, remember that a distribution describes the possible values of a variable and how often these values occur. The easiest way to picture a distribution is with a graph, such as a dot plot or a histogram. And of course, every statistic has its own sampling distribution. Again, they are just meaning if I was measuring the mean, or if I was measuring the standard deviation, of course those different statistics would have their own distributions. All right, so here's an example. It says John and Carol have 4 grown sons. their heights in inches are 71, 75, 72, and 68. So list all 6 possible SRSs. Those are simple random samples of size n equals 2, and calculate the mean height for each sample and display the sampling distribution of the sample mean on a dot plot. So this is an example of a very, 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 very small population. The population would be John and Carol's 4 sons, and they had the heights of 71, 75, 72, and 68. So imagine now if I wanted to know, like, what's the average height among this population. Well, I know that it doesn't make a lot of sense here. There's only 4 numbers. We could just average them. But imagine if this was a much greater population. Well, this whole process, sort of on the small scale, sort of lets you know how we do it on the big scale. So what we would do is we would take every single possible sample. In this case, we're just choosing size 2. So what would my first sample of size 2 be? Well, it would be the 71 with the 75. And then with just those 2 numbers, I can average them pretty easily. You just add them up and divide it by 2. So that would give what? 146 divided by 2 is 73. So now it feels like, okay, maybe on average, the population is on average has a height of about 73. But we do this again. We take another sample of size 2. I'll keep this person who's 71, but this time we'll sample the 72 to go with it and average that out. This one we can do in our heads. It's 71 and a half. Okay, then again, this person who's 71, we could sample that person one more time, but this time sample them with the person who's got a height of 68. And that would be 69 and a half when we average it out. But in this way, what we're doing is we're building up that sampling distribution. Here's just 3 of those average heights right there. And I'll stop doing this now and just kind of show you the answer. But here's all of those samples. Okay, and so you can see that distribution kind of forming. And so all of these averages now give me some idea of what the average of the population would be. And then if I want to see this better, then I can use a dot plot to sort of see my distribution. And it certainly seems like the average of the averages, or the center of all those averages, seems centered around about 71 and a half. It's pretty evenly distributed. Again, we don't have a heck of a lot of data here to talk about the shape of the display, but it certainly seems to be pretty evenly distributed around 71.5. So all this data that we sampled does start to give us an idea of what the population would look like. So hopefully that idea makes sense. Okay, so again, it says every statistic has its own sampling distribution, and of course it does. If they're different statistics, then they're going to have different distributions. But just to kind of drive that point home, they're going to be grabbing all 6 of the samples of size 2 and measuring different statistics about them. So looking here, here's all 6 of those samples of size 2, but this time they're measuring the sample range. So from 71 to 75 is a distance of 4. 71 to 72 is a distance of only 1, and then 3, and then 3, and then 7, and 4. But there's what that distribution looks like. And so how does that compare to the other one? Well, I happen to have it right here. Almost seems a little silly here to point out that they're going to be different, because of course they are, because they're different statistics. But just so you can see, of course the points fall in different places. If one statistic was skewed right, the other statistic could very easily be skewed left or perfectly symmetrical. The means could be completely different. So that's the only point here that I think they're trying to drive home, is that from a certain population we could draw many different statistics, and of course those statistics could look very different from one another. Okay, next thing is a caution here. You have to be very specific when you use the word distribution, because there could be multiple distributions for a given setting. Okay, so for example, what do we mean? Well, we already talked about the distribution of height in the population. The population was the 4 sons, and so the distribution of their heights would be literally just all 4 of their heights. But sometimes instead of the distribution of the heights in the population, we would talk about the distribution of heights in a particular sample. And so this, I think, was the first sample we drew, the 71 and the 75. But there were 6 different samples we drew. So sometimes you're looking at the distribution of the heights in just one particular sample. And then lastly, you might talk about a completely different variable. You might be talking not about the distribution of heights, but about the distribution of the sample ranges. And we might do that for all possible samples and see all 6 data points, or we might do it for just a few samples at a time. But again, you have to really describe the distribution very well. So you're talking about the distribution of what statistic and in what group. Is it the parameter from the population? Is it a statistic from a sample? If it's from a sample, which sample? Blah, blah, blah. You get it. Moving on. All right, using sampling distributions to evaluate claims. Sampling distributions are the foundation for the methods of statistical inference that you'll learn about in chapters 7 through 10. Knowing the sampling distribution of a statistic will help us know how much the statistic tends to vary from its corresponding parameter and what values of the statistic should be considered unusual. So let's look at what that's about. So a lot of text here. I'm going to read through it because it's important we understand it, but it says, problem, at the beginning of class, Mrs. Chauvet shows her class a box filled with black and white beads. She claims that the proportion of black beads in the box is 0.50, meaning it's 50-50. Half of the beads are black and half of the beads are white. To determine the number of homework exercises that she'll assign that evening, she invites a student to select a simple random sample of n equals 30 beads from the box. The number of black beads selected will be the number of homework exercises assigned. When the student selects 19 black beads, the students groan and suggest that Mrs. Chauvet included more than 50% black beads in the box. Let's kind of unpack that, make sure you understand what's going on. If the proportion of black beads was 50%, then what would have been the expected number of black beads pulled if they pulled 30 beads? Well, the expected value, like we talked about last chapter, would be the number times the probability. So they should have expected to get maybe 15 black beads. Maybe they were expecting to get lucky and to be sort of below that value and only get 12 or so. But the question is it that unusual to have gotten 19? Does 19 sort of differ from our expected value by so much that you doubt the claim that this thing was 50% in the first place? Do you feel like Mrs. Chauvet filled that vial or that box? Sorry, I don't know why I keep saying vial. There was a picture before of like a glass vial filled with beads. This is just a box. But do you feel like she's some like criminal mastermind who's telling them, oh yeah, it's only 50% black beads, but really it's 75%. So they end up with extra homework. So that's the claim we want to test is it really plausible that there was only 50% black beads, but then you still pulled out 19 beads? Like already that shouldn't seem like it's too crazy, but let's see. Let's test and find out if 19 is higher than our expected value by enough to make us doubt this claim in the first place. So to continue reading, it says to determine if a sample proportion of 0.63, that's the 19 out of 30 gives us a 0.63% sample proportion. So does that provide convincing evidence that Mrs. Chauvet cheated and the class simulated 100, to figure it out, the class simulated 100 simple random samples of size 30, assuming that she was telling the truth. That is, they sampled from a population that really did have 50% black beads, and for each sample they recorded the sample proportion of black beads. The results of the simulation are shown below, so here's the results. Alright, so first of all, it says there's one dot on the graph at 0.77. Just explain what that dot represents. So just making sure we know how to read the table. The one that's at 0.77, here's 0.7, so this must be 0.77. What does that mean? Well, I'll take you over here and I'll show you the answer. That 0.77 represents the fact that in one of our simple random samples of size 30, the number of black beads chosen was 77%. So again, here's this worded by the textbook, a little differently from how I worded it, but basically what you want to say is that one dot represents that in one of our simulated simple random samples of size 30, 77% of the beads were black. That's the meaning of that number. So just make sure you can put that into words. Part B says, would it be unusual to get a sample proportion of 0.63 or higher in a sample of size 30 when the population parameter proportion was 50%, and explain? Well, this goes back to a previous chapter. We've done this before too. What we would do here is we would do these 100 samples, and we would just see how many times we actually get a sample where we're getting 0.63 or higher. So looking here, this is 0.6 obviously, and this is 0.7 sort of obviously, but what are these numbers in the middle? They're not labeled, so you have to be a little bit crafty about this. But look in here, I see, there's the 0.4, and then there's only 1, 2, 3 carrying us up to 0.5. So apparently these are spaced by about a third, and a third is 33%, so call me crazy, but this first line of dots is going to be at like 0.4 plus an extra 33%. So 0.433. And then this one would be at about 0.466. And then the next one would be at about 0.5. All I'm trying to say is 0.46, you can rest assured that that's this very next stack of dots coming after 0.6. So those guys are about 0.63-ish. So I do want to count those as being at 0.63. So how many are there? I see, what color is going to stand out here? How about orange? I see 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's 9 out of how many attempts? 9 out of 100, right? Because how many simple random samples did we draw? 100. So what percentage of the time are we getting a proportion that is this high or higher? 9%. And what has always been our universal cutoff, at least up to this point? Our universal cutoff for a result that is strange is a result that only occurs 5% of the time or less. So this is not strange. Let me show you what the textbook says. It says, no. It says it's not unusual to get a sample proportion that is this high, because in the 100 simulated samples, 9 of the simple random samples included at least 63% black beads. So we are not shocked by this. The kids might have been shocked by it, and they might have moaned and groaned because they're looking at extra homework, but mathematically it is not weird for us to have gotten an answer that was that much higher than our expected proportion. All right, so part C says, based on your answer to part B, is there convincing evidence that Mrs. Chauvet lied and cheated about the contents of the box? Again, you would say, nope. We're saying no because the probability from part B, the 9% probability, it's not that small. It's plausible that the proportion of black beads in the box truly is 50%, like she said it was, and that the students just got a sample that was this much higher just by chance alone. It's just up to sample variability. We said that before, and that's a key word you should probably include in your answer, that getting a sample proportion of 0.63, even though the population proportion was way down at 50%, that's not that weird, and that is attributable to simple sampling variability. It does not provide evidence that Mrs. Chauvet lied about the population proportion. All right, I think that brings us pretty close to the end. I hope that all made sense. There's a couple of practice problems for you to do now, and if you get them right, then you're in a good place. If you get them wrong, then you should probably see me for help, or just ask me questions when I see you again. But here those problems are now. I guess I'm going to read it to you just because. It says, during the winter months, outside temperatures at the Starnes' cabin in Colorado can stay well below freezing. Freezing is 32 degrees Fahrenheit, by the way, or 0 degrees Celsius, but the problem goes on to talk about Fahrenheit. But it can stay well below freezing for weeks at a time. To prevent the pipes from freezing, the Starnes set the thermostat at 50 degrees Fahrenheit. The manufacturer claims that the thermostat allows for variation in home temperature that follows a normal distribution with a standard deviation of 3 degrees Fahrenheit. So it could go down by 3, up by 3. To test this claim, Mrs. Starnes programs her digital thermometer to take a simple random sample of size 10 readings during a 24-hour period. The standard deviation of the results is 5 degrees Fahrenheit. So we've got kind of the same thing we just saw with Mrs. Chauvet's class. She said that she had 50%, then they did a random sample, and you would have thought that you would have gotten about 15 beads, but instead they got 19. 19 is bigger than 15, so they wondered, maybe the population parameter isn't really 50%. Maybe it's more like 60%, and that's why my sample is up around 60%. The Starneses are now thinking the same thing. They're thinking that their thermostat allows for a standard deviation of 3, but their sample had a standard deviation of around 5. So maybe the thermostat actually varies by more than just 3, up or down. Maybe it varies by more. So we are supposed to kind of attack that question. So the first question is sort of the easy one. You just have to describe the population in words and the sample in words, and then describe the parameter of interest, describing the population, and then describe the statistic of interest that is drawn from the samples, and do that in context. And again, pause the video if you want to do that now. Pause. Okay, too late now. Here comes the answer. Yoink. So what's the population? The population is all possible times during a 24-hour period. Remember, what's Mrs. Starnes doing? She's programming her digital thermometer to take a simple random sample of n readings during a 24-hour period. So in that 24-hour period, it takes 10 readings just randomly at random times. So the population would be every single possible time during that 24-hour period. Now the parameter, meaning the number that we care about, right, is standard deviation. And so the parameter would be the true standard deviation of temperature readings at every single possible time during the 24-hour period. Now that's almost literally impossible for us to figure out, right? I mean, there's a million bazillion different times during a 24-hour period that we could actually take a sample. But imagining if we did it, if we somehow found the standard deviation at every possible moment, then that's what the population parameter would be. Now, what's the sample? The sample is the simple random sample of 10 times taken during the 24-hour period. And the statistic would be the sample standard deviation of temperature readings, which is, in this case, the 5%. So moving on to actually testing the claim, number 2 says, would it be unusual to get a sample standard deviation of 5 or higher in a sample of size 10 when the population standard deviation was only 3? And it says explain. So I'll show you this. Now obviously there's some background here. To test this claim, somebody had to actually do, it actually says up here, I'm supposed to read this with you first. But so to test this claim, I'll shrink this down again so you can't see it. But to test this claim, it says, suppose the thermostat is working properly and that the temperatures in the cabin really do vary according to a normal distribution with a mean of 50 degrees and a standard deviation of only 3. Then the dot plot below shows the distribution of the sample standard deviation in 100 simulated simple random samples of size 10. Remember, Mrs. Starnes took a sample of size 10, so our 100 simulations have to all be of size 10 as well. And this is how they sort of fell. It says, would it be unusual to get a sample standard deviation of 5 degrees or higher? Well, let's go and check it out. How many did we get that are 5 or higher? And it's 0. We never got a single one that was 5 or greater. So, what's it say? It says, well, yeah, it would be very unusual to get a sample standard deviation of 5 because we just did 100 simulated samples and none of them had a sample standard deviation of 5 or higher. So based on our simulation, the probability of getting a sample statistic or a standard deviation that was greater than 5 is 0. But it happened though. It did happen. Mrs. Starnes found it. So what does that mean? It says, based on your answer to question 2, is there convincing evidence that the thermostat is more variable than the manufacturer claims? It would seem so, right? It would seem like if the standard deviation was truly only 3, then we would never have gotten a sample that was that high. That makes me think that probably the standard deviation isn't actually 3. The standard deviation is probably 4 or 5, or maybe even 6 or 7. But it really can't be 3, because if it was 3, then the probability of getting a sample standard deviation that was that high is like 0. So how'd the textbook put it? It says yes. Because the probability from 2 is so small, it's not plausible that the true standard deviation could possibly be 3, and Mrs. Starnes got the sample standard deviation of 5 by chance alone. It's just not possible. So where's the mistake? The mistake must be in assuming that the population standard deviation really was 3. It must be something higher. That's the idea there. All right, again, I hope this all made sense. It's 36 minutes, so that feels about right for a lecture in a 42-minute class. Let me know what you think of this. If you can if this video was good, bad, and different, if this kind of thing works for you, if you can follow along with this better or worse. I'd love to have some feedback on how this went for you. But anyway, I'll see you again soon. Bye.